Something falls inside. It is hauled to the focal endpoint called the peculiarity, where everything gets crunched. However, imagine a scenario in which we let you know that's not precisely the way dark holes work. So, what's the peculiarity anyway? And what really is on the other side of the pitch-dark curtain? Prepare to find a mind-twisting universe of dark holes where the truth is way more interesting than any fiction. Dark holes are complicated space peculiarities. Every little thing about them is muddled. When a huge star, around 10 to multiple times more massive than the Sun, all debilitates its fuel, the equilibrium between gravity and pressure breaks down. The star implodes in on itself and goes cosmic explosion. The issue with our current understanding is that we utilize unique speculations to make sense of peculiarities occurring on different scales. There's quantum field hypothesis, which functions admirably to explain the mind-boggling behavior of particles ranging from atoms down to the smallest subatomic structure blocks of matter. Apply this hypothesis to cosmic scales, and it's of no use. For that task, researchers resort to Einstein's general relativity. Pick the right hypothesis and calculations create correct responses. However, dark holes are tricky. At first, they are cosmic objects, huge stars, and then they rapidly shrink to much smaller, sometimes quantum sizes. For example, in order for the Sun to become a dark hole, it would need to be crushed to the size of pretty much 1.8 to 9 kilometers in radius. Theoretically, you can turn any object into a dark hole. There's a recipe that lets us know how much something must be crushed to become one. This limit is known as the Schwarzschild radius. Assuming you wonder exactly how minuscule our planet would need to be to transform into a dark hole, imagine the whole Earth as a ball with a radius of 0.35 in 0.88 centimeters. But imagine a scenario where an object's radius is 0. Ordinary calculations, both mathematical and physical, become insignificant. So we call this peculiarity a singularity. But does such an idea genuinely show up in the actual world? Let's try to break it down. Think about this mental study. If you needed to make the simplest version of a dark hole, you'd start with minuscule pieces of matter floating around in space. They don't push against each other but just hang there. So they're like little bits of dust floating very close to each other without moving around much. However, in space there's gravity, so it starts pulling everything together, reducing space between dust particles. After some time, little bits of dust start to crush increasingly tight, ultimately coming to where their combined mass and gravity grow so intense that space around them starts to pack. This creates an event horizon, a sort of boundary that allows things in but doesn't permit anything to get out. This sort of dark hole is known as a Schwarzschild dark hole. It has mass, which is exactly how much stuff went into making it, but it doesn't have any electric charge or turning motion. Now contemplate what happens when you cross the event horizon of such a dark hole. For exploration, let's assume it's huge enough for you to enter with a spaceship. Once in, you panic and try to get out by firing engines to advance quickly back out. Physics says that no matter which direction the ship is facing, you'll still be drawn toward the central singularity. To figure this out, imagine a long, narrow hallway with no way out except through a door at the end. When you step into this hall, the door closes behind you, and there's no way to open it again. The hallway has a moving walkway, similar to the travelator in an airport, taking you forward at the speed of light. Regardless of which way you try to move, either running in the opposite direction of the walkway or moving sideways, you'll still be carried forward by the walkway. This is how researchers think dark holes act. However, spacetime gets way more complicated when you have a mass that rotates. So far, we only know about the existence of dark holes that have angular momentum or spin. They form from the collapse of rotating massive stars. As matter collapses, the rotation is conserved, leading to the formation of a spinning dark hole. Quantum mechanics was created to explain the abnormal universe of miniature scales. Instead of giving us answers, it led to more uncertainty, like fluctuations in the fabric of spacetime. These quantum fluctuations play a huge role concerning event horizons surrounding dark holes. We've all heard that nothing can escape a dark hole, but this is where things get tricky. Near an event horizon, particles and antiparticles suddenly pop in and out of existence, destroying each other immediately. However, imagine a scenario where one of these particles figures out how to escape the fortress of a dark hole. The late, Great Stephen Hawking explained this with his hypothesis of Hawking radiation. When a particle-antiparticle pair forms close to the event horizon, one of them falls into the dark hole while the other escapes. The free particle takes energy from the dark hole. Given enough time, numbers hard to imagine, like 10 to the power of 68 to 10 to the power of 103 years, a dark hole would dissipate completely, leaving nothing behind. But if nothing remains, where does this limitless singularity go? In the real universe, there are no such things as boundless values, or at least we haven't found any yet. So when researchers make estimations that lead to infinity, it means there's something wrong with the hypothesis. It's too simply stick to be applied to extreme cases. Imagine a guitar string gently plucked at its resonant frequency. According to the simplest model of wave behavior, the vibration of the string would grow exponentially over time. In theory, it would vibrate past the moon, the stars, out to infinity, and then back. But although this is what the model predicts, it's not what happens in reality. The appearance of infinity in the model says it's distorted, and there are certain limitations while working perfectly to explain string vibrations when they're small. You still need a better hypothesis to avoid infinite values. So what does this mean for our understanding of dark holes if singularities aren't real? Perhaps at the center of every dark hole lies something else, something beyond what we can fully grasp. Yet, as always, scientists have some ideas. According to Penrose's hypothesis, singularities are unavoidable in general relativity. Anything that moves in space and is only experiencing the effects of gravity should follow a specific path, a so-called geodesic. Essentially, it's the shortest, most efficient path both spatially and temporally. The idea is that space-time is all organized, like the universe is one huge fabric, and its structure is directed by these geodesic lines, some of which are straight and others curved. These paths are continuous, like a line drawn over a spherical object. But Penrose proposed that geodesics should converge inside dark holes, ending at their centers, which means paths of spacetime itself end, and you have a singularity or infinity. Stephen Hawking believed that this is how the Big Bang started, as a singularity, or in other words, geodesics that follow back to one single point. Although a recently published paper by Roy Kerr suggests a significantly different perspective on dark holes, the spin of matter changes everything. Instead of a single event horizon marking the boundary beyond which nothing can escape, rotating dark holes have two distinct horizons, an outer horizon and an inner one. These horizons are like invisible walls marking areas where the gravitational force becomes too strong for even light to break free. Rotating dark holes also have something called an ergosphere, whirling zones surrounding a dark hole where spacetime itself is dragged along by its spin faster than the speed of light. If you happen to be there, no matter how diligently you try to stay fixed, it would be to no avail. In a way, these ergospheres are like whirlpools in spacetime, impacting the movement of neighboring objects that come in contact, creating very bright light because of how insanely fast things move there. If an object manages to escape an ergosphere, it would leave with much more energy than it entered with. In theory, this mechanism is the source of nearly boundless energy, though figuring out how to extract it seems an impossible task. And then again, there's still the singularity. Although it doesn't have a point-like shape, but rather a ring-like structure due to the impact of angular momentum that smooths it over. Here's a simplified way to picture this. Imagine a drop of paint falling onto a piece of paper. If the paper is fixed, the paint forms a single dot. However, if you turn the paper fast as the drop falls, the paint fans out, creating a ring-like shape. So, if matter falls into a dark hole along this confusing path, its way isn't like a simple circle that stays in a single plane. Rather, it moves all over the place, like a bee humming around in the air. Over time, the particle path fills up a three-dimensional shape. Instead of adhering to a flat path, particles around turning dark holes move in all directions, painting a sort of donut shape in space. Particles pulled in by a turning dark hole won't just cross the event horizon, going directly into the central singularity. It's not like dropping a stone into a lake where it sinks directly to the bottom. Instead, it's more like throwing a leaf into a strong wind. The wind's whirling motion carries the leaf in various directions, sometimes pushing it closer to the ground, other times lifting it up. Called Kerr dark holes, these rotating celestial beasts don't have real singularities. and matter doesn't necessarily end up falling inside their central singularities. Instead, past the event horizon the outward force creates.